Okay, we are now recording. Amazing. Okay, I'll go ahead and get started now that I'm recording and it's 10:04. So what I'm gonna do is I made a really in-depth review document, um, and I'll be going over it and I'll post it into the Discord and here, probably afterwards because I have to transfer things. But yeah, I'll be doing that and then going through a couple of practice problems. I only made a few, but they're not too difficult. So once you get one, you should be able to get the rest of them. So yeah, that's kind of the game plan. And y'all can feel free to ask any questions or anything like that in the meantime. But let's jump into it. Okay. Okay, so I kind of organized it. It's loosely based on, I had an outline that I showed you guys during one of my lab sections. Well, I guess my last lab that I taught. I showed y'all kind of a general outline, and this is kind of based on it. I went through the exam and kind of also structured the order and information kind of based on what types of questions you're going to see. So starting first, we have error, big concept. We have two main sources of error in all of our numerical computations. We got round off and truncation. They're kind of hard to differentiate at first, but round off is essentially just trying to store too much data in a finite space, and then truncation is the result of cutting an algorithm short. And so super handy little thing to know. If you remember, Taylor the elephant has a trunk. You know that when you cut a Taylor series short, so essentially because you can't reasonably, since Taylor series is so long, you can't reasonably compute every single component of the series. So you have to chop the algorithm at some point. And the error that you get when working with Taylor series is most prevalently truncation. So that's like the big main thing of errors. The next major topic is number storage. So Luke, you asked this during lab, and so I went back to make sure that I wasn't giving you guys the wrong information. And so we were both right. It depends on what type of number you're storing that
Like a
determines.
float versus an integer.
Yes,
Yeah,
exactly.
that's what I thought it was.
Yeah, I had it in my other review. I think I just said 64. Like I didn't specify between the two. So yeah, storing real numbers is 64 bits, and then integers is 32 in double precision. And it's going to be half of that, I believe, for single precision. But yeah, and then I just redrew the number lines for you guys. Super handy to know, extremely handy to know. Wink wink. And so I did it in both double and single precision, so you guys can kind of visualize it a little bit more. Massive pro tip though, I spoke to my lab about it quite a bit, but the strategy when you see kind of question that's asking you, the largest or smallest number that you can store, first thing you look for is what precision, if it's single or double, and then look what type of number, if it's real or an integer. And because I know a lot of people, even I messed it up once in like a quiz, I think last semester. It's easy to just skim it and be like, oh, I know double is 10 to the 308, but you gotta really sit down and look, make sure that you're not bamboozling yourself because you didn't read. So yeah, that's a big tip. I think you have to know this. I'm like pretty sure you have to know what happens when you try to store too large or too small of a number. Typically, rule of thumb, attempting to store numbers smaller than the smallest number you can store is a non-fatal error. So it'll just reset your value to 10 to the negative 308 without crashing. But attempting to store a real number larger or an integer larger than your max that you can causes a fatal error. So essentially you're just going to crash your program. um, though a little side note about this, you have to know what happens. Like this is the general rule of thumb, but technically this isn't the case all of the time. Um, so for the purposes of this test, know this, these three things, or like these three main bullet points. But in the real world, that's not necessarily the case. So yeah, just bear that in mind. So then the next big topic, we talked about it a lot in lab, machine epsilon, smallest value that can be added or subtracted from zero and still be distinguishable from zero. Rule of thumb, single precision, it's 10 to the negative 38, and double, it's about 10 to the negative 308. It's not exactly that, because if it was exactly those, then it would be zero. So it's, slightly different than that. But I feel like that's pretty obvious. And do know that you can't, I don't remember if I wrote it later, but that computers approximately store zero in single precision as 10 to the negative 38 and 10 to the negative 308, because it's the smallest storable number, and zero can't be precisely stored. Next big thing is converting decimal to binary. I made like a little handy dandy, I guess you could call it an algorithm for how to do it. There's general steps for depending on what type of number you're working with. So say you're working with a number greater than one, but it doesn't have like anything after the decimal point, like it's just a whole number, then you follow these steps. I think I worded it decently okay, I hope. But yeah, essentially you're just dividing by two. Well, technically you're taking the modulus of the number, and if the remainder is one, then it's going to be one in that place. If it's zero, it's a zero. But every time you're dividing by two, over and over and over, and then you flip it, because essentially the way that that binary is each place to the left of the decimal represents two to the 0, 1, then 2, then 3, all the way up through n. So that's why you have to flip the number. And then you kind of have to do the opposite when it comes to numbers that are less than 1. So you're multiplying by 2 every time and seeing if you can subtract 1. If you can subtract 1, then there'll be a 1 in that place. And if you can't, it's a 0. And this technically just continues for a very long time. it keeps going. Technically, there's like a rule to stop. It's until the resultant fractional part is 0. In this case, you don't have to flip it. It's you literally just like, see, like here, you're going 0, 1, 0, 1, 1, 1, and that goes straight into the answer to the right. And then when you have numbers that are greater than 1, so like say you have like 1.32, for example. So I did a little example for y'all. Let's see. Oh wait, did I write 1.32? Probably meant to write 17.32. Oh well, I'll fix that. 17.32 would be the combination of this 17 and then, wow, I totally goofed. If you can't tell, it was a little late when I did this. Also typo. 17.36 would be the combination of this and this next to each other. So, oh wait, no. I did do it right. We're good. It would just be that. So yeah. It seems kind of complicated if you've never worked with it before, or at least it did to me. So that was just kind of my handy dandy guide to converting from decimal to binary. But yeah, so those are like big number storage things. Why did I jump right into this? Oh, I probably snatched it from a different study guide. Or actually, can I not see the chat anymore? Feels kind of bad. Oh, yes, I can. Iconic. Okay. Does anybody have any questions about anything I've talked about before I move on? guess I'll take that as a no, I suppose. All right, fair enough. Binary back to decimal. Is that on the test? I recommend knowing how. I don't recall if you have to on the test. But if you know how to go one way, I mean, okay, Luke, I recommend knowing how just in case, just to be safe. But I don't recall exactly. Because there's like multiple test banks. There's a lot of questions. So there might be one of those in there. So I recommend being able to go back and forth. Going from binary to decimal, I feel like is a lot easier because you're literally just adding. So didn't mean to do that. Let's see, where's my little chart? This little guy, well, at least to the left of the decimal is easier because it's literally just each one represents that place's respective 2 to the whatever. So if you have a 1 immediately to the left of the decimal, you're just adding 2 to the 0, and you're just adding as you move forward. So the right side's a little trickier, but I don't know. I think you guys got it. Any other questions before I continue?
This might be a little confusing, but I'm just trying to get my head around it. When you write like a binary number, you write it from, like your example, you would write it from the bottom to the top, correct?
So for the values that are to the left of the decimal, you write from bottom to the top. Yes.
Okay.
But when it's to the right of the decimal, you're writing from the top to the bottom. Which
Okay.
sounds weird, I know, but it has all to do with like what the different 2's represent.
Okay, thank you.
Yeah, of course. Anything else? And again, this will be posted somewhere. I might post it even in the web courses. We'll see. Just so it's a lot. It took me a really long time to make this, unfortunately. But it'll give you all a chance to look it over again and really digest it, I think. So if there are no other questions, I shall continue. Okay. Ooh, I should probably close this so I can see. Okay. Did I really just skip through? Oh, no, I didn't. I just didn't underline that one. Okay. So that kind of closes off this section regarding number storage. And now we're talking about fixed point form, a big topic. It sounds complicated sometimes when you're told about it in like lecture and stuff, but it's really not so bad. Essentially all you're doing, so you're given an equation, right? And it's like, or a function, I suppose. So for example, you got this f of x equals x squared plus 7x minus 28. If you're asked to put it into fixed point form, all you're doing is rearranging the function so that you have an x on the left, just a single standalone x on the left of the equal sign, and then everything else goes on the right. And so with some cases, you can do that multiple ways, and they're all right. So with an x squared as being your highest order, then you have 2 ways. With an x cubed, I think you have 3 ways. You might even have more than that. But just know that there's multiple ways that you can do it. But essentially, the form is x equals g of x. And know what would indicate a good initial guess. So yeah, that's like mostly it on fixed point. Pretty straightforward, but I do recommend knowing that. I think it might even be on your formula sheet. Your formula sheet is your best friend on this. Should it be square root? Did I write it wrong? Probably. Wait, where? Square root 28 minus 7x. Yes, you're absolutely right. I didn't switch over the the negatives. Yes, you're absolutely right. I'll fix that. I wonder if I can fix it now. Let's see. Because I'm on my surface. It's a lot harder when it's like standing up. Thank you. I appreciate the there. That should be right? I think. Did I not do it on the other side either? Bruh. Sometimes my brain do be not the best. Okay, hold on. Yeah, so this would be negative. Oh, God, this is so difficult. Okay. Technically, I could just be like, yeah. There. All better. So yeah, that's that. Thank you. Who was it that pointed it out? Was it Hunter? Luke? Somebody? Whoever. Yeah, Hunter. Thank you. I appreciate it. So yeah, another big point. I don't really feel like going super in depth on it because it's pretty straightforward and the equations are literally at the top. But finite difference, forward, backwards, and central. So you should know not only how to do them, but also what type of errors they have, like, or at least be aware. I think it even says it on your formula sheet. Like literally, your formula sheet is your best friend on this. Wouldn't the square root not be good because after x equals 4, square root, or does that not matter? I have to think through that question. So essentially, that's a difficult question, Connor. So not necessarily that it wouldn't be good, it just limits what solutions of x you have. So I guess since it is on your formula sheet, it's not like I can't say it. But determining what a good initial guess is if g prime of x evaluated at some value of x is less than 1 but greater than 0, would mean that you have a good guess because it's converging. So realistically, like if you plot that graph I did to make sure that it does have a solution, it's not necessarily that the square root's not good. It just is kind of like a limiting thing. This is definitely not a fantastic example. I just kind of made up a polynomial on the fly. I was like, yeah, this seems like this could be right. And I didn't want to give you guys a double root because that kind of gets a little screwy sometimes. So yeah, I don't know if that really answered your question, Connor, but it was an attempt. Okay. So I wonder, okay, yeah. So this is kind of like an overview of some of the, I don't know, I guess test layout, I suppose. So you're gonna have 25 questions. 15-ish of them are going to be like somewhat math heavy, and the rest are conceptual. 15-ish, I say that because it's not exact. But of the math ones, so what's gonna happen is you're gonna have your chunk of questions, it's like 10 or whatever, that are more broad conceptual questions. And then it jumps into, you get 2 big problems and you're either gonna have one, well, there's a couple of combinations, I suppose, that you could have. But one of the problems is either going to be Newton-Raphson, secant, or bisection, and then the other one is going to be another one of those 3. So know how to work all of them. And you'll want to know how to, like do the estimated root update after each iteration, as well as finding the residual and the convergence in each scenario. Also know the rate of convergence for all of the different types of root finding methods. And fixed point iteration is kind of integrated into those big questions. Gosh, sorry, I keep getting notifications. So yeah, so make sure to know, like, those are the big math heavy topics. Everything else that we've kind of covered already is more conceptual for the most part, except for finite difference. It's math, I think. Well, math and conceptual. But yeah. I think that covers, that's kind of just broad. I snatched this from my review last semester. Okay, and so now we get into, let's see if I can zoom out a little bit, the actual methods and talking about how to do them. As I said before, and I keep saying it over and over, your formula sheet is absolutely your best friend, because they literally put in, well, I say they, Dr. Kasab literally put in not only all of the formulas that you need, but also even visual graphs to kind of help you with each of the methods. Like this bisection method graph is in your formula sheet. He has a nice little table that has your residual and convergence, and he has that for all three root solving methods, which we love to see for y'all. We really do. But essentially, bisection method, what you're doing is you've got your function and you're looking at it, and you know that at one point A, you have your bounds A and B. One point A is going to likely be, a negative value evaluated at that A point, and then a positive evaluated at the B. So you know that there has to be a root somewhere between A and B. And all you're doing is you're going, okay, so I've got A and B. We're going to go at the midpoint, and then we're going to look to see if that's a positive or a negative. If it's a positive, or if the function is positive at that midpoint, there we go, it's a better way to word it, then that midpoint becomes your new B. And so now you're evaluating from your initial A to your new B, which is your midpoint. If that midpoint happens to be negative, then that is going to become your new A, and your original B is going to stay the same. And you just keep going midpoints and trying to find, keeping your A negative and your B positive. And you get closer and closer and closer to this 0. And you find your residual each time by evaluating the function at this new midpoint of the iteration and taking the absolute value. And then your convergence is just your new, whatever, B minus A over 2, an absolute value. A very helpful equation, I think this might be on your formula sheet too, to know. I recommend looking at it, maybe even, actually, did I? Yeah, I did make a sample problem for a bisection. So I recommend trying to make your own, or at least having an idea of how you would handle this equation right here. But you can find the number of iterations required with bisection method by using that equation. So say you're given a tolerance of like 10 to the negative 5th, and you have bounds B and A, you can find how many iterations it's going to take to reach that tolerance, which is kind of cool. Pretty sure it's based on error too. Yeah. Why did I have to write that so big? Now I have to super zoom out. Okay. Okay, there we go. It's closer. So I hope y'all know how to do Newton-Raphson by now, but especially since we're doing it in project, but neither here nor there. So each iteration, you're updating your estimated root by taking your previous estimated root and subtracting the function evaluated at your previous root over the derivative evaluated at your previous root. And so you get your, your residual, which is this R sub n. It's the residual and convergence are the same for all three methods. The equations might look slightly different, especially with bisection, but it's the same. And it's pretty much the same with most of the rest of the methods that we work with from here on out. Like we'll do a nonlinear Newton-Raphson. I'm pretty sure the convergence and residual are the same formula for that too. So highly recommend remembering those things. They're pretty simple concepts, so it shouldn't be too bad. And this is like a kind of step. I have the steps laid out better with the practice problems, and I'll show you all then. But yeah. Oh, and do know this right here, this little red chunk. Very important. Very important. You're using your fixed point theorem to check if your initial guess is a good one or not. And then secant is just Newton-Raphson, but you're replacing the exact derivative of the function with a backwards finite difference approximation. So especially with cases where maybe the function is very complex, you can use just two initial guesses and the function instead of having to have the exact derivative. I talk about secant twice, apparently. Oh, this is because I snatched it from somewhere else. But yeah, and it converges. So secant, actually, I think I wrote it above, but this formula is mildly confusing. I also work it a little bit better in the other one, but let's see, where's my convergences? Yeah, rates of convergence. No, Newton-Raphson is quadratic, except it's linear with a double root. So say you have a function that's like f of x equals x minus 2 times x minus 2, then that's going to be linear. But in most cases, it's quadratic. Bisection converges linearly, and secant converges superlinearly. So I'll also know that as step sizes, like general practice, as step sizes get closer to 0, truncation error decreases and round off error increases. So yeah, and I think that might be all of it. Yes. Okay. Y'all have any questions before I go to the practice questions?
What do you mean as step? Can you go back to where it said step size, truncation, and round up? I was going to ask you about that.
Yeah. Okay. So I think that one applies more for finite difference approximations. I know it's like weirdly thrown in there, but that's just like a helpful little tidbit. I don't even think he's going to ask you about it, but in case he does, yeah, that's more specifically for forward, backward, and central finite differences, because that's where you're actually dealing with step sizes. So yeah, because like central finite difference error is proportional to step size squared. Forward is step size, or proportional directly, linearly, whatever, to step size, and same with backwards. But as those step sizes get closer to 0, truncation error decreases and round off increases. Anything else? Also, if I breeze through that too fast, I apologize. I can go over things again if you want. Okay, I'll take that as a no for now. Okay, let's see. And here are our questions. Okay. So this is the kind of solutions to the practice questions that I dropped in the Discord. Yeah. So we already kind of did this one. That's just like another. I hope I didn't screw it up again. Did I? I did it again. Okay, don't be me. I think I did it right on this side, but not on this side. Oh, goodness. Okay. So yeah, don't make the same error that I made. It is going to be multiple choice, so it's not like, well, I guess there might be an option that screws with you, but it's unlikely. So yeah, keep an eye on that. Don't be me and make the same thing over. Okay, so yeah. First one that we work through is Newton-Raphson. So this is kind of my steps anyway, my process when I'm going through these root solving methods. What I do is I kind of lay out what I have. So you have your function, and that's kind of given, and you have your initial guess of x of naught is 3. So decent practice is with Newton-Raphson is to take the derivative. If it's not given, it might be given. I don't necessarily know. You take your derivative, your exact derivative, write that out. Then you find the function evaluated at your initial guess in the derivative evaluated at your initial guess, and just like write that down so you have it for the first iteration. And then, so working through it, you got your x of n plus 1 is x of I minus f of x of I over f prime of x of I. So that ends up being 1.4. And finding your residual, yeah, you just find of this 1.4 function of 1.4. That's that convergence is that decently straightforward. And your equations are on your formula sheet. So I believe in you guys. And then being able to do it again. So typically, somebody knocked on my door, sorry. So typically I would even write more than I did. Typically, you can go back and you can be like, okay, well, if the residual was this and you made sure you wrote it like inside that brackets, you're going to know the function evaluated at that is going to be this. And so you can go and reuse some of these values. But yeah. But yeah, I don't know. I feel like it's decently straightforward. And if you grasp the project 2 at all, or even just look at the code, it could help you understand kind of the process for Newton-Raphson and secant. But yeah, and I'll post these answers so that you guys can see them and like work through them on your own. I'll post the blank one and I'll post the, sorry, I think somebody just came in my apartment. Anyway. Sorry, y'all. Weird. Okay. Anyway, what was I saying? Oh, okay. So the next question that I do, bisection method. So a little pro tip for you guys. I highly recommend use an approach that making a table. You can kind of do the table however you want. This is how I do it. I usually just go in order of X, like all of your guesses and putting it in there. But you could also, if you really wanted, you could be like, okay, you put A at the top and then you put B at the bottom. And as you work your way in, you could kind of fill in the gap between them. That's entirely up to you, but it's still nice to keep everything documented so you don't get a little lost, which is pretty easy to do because your bounds are always going to be determined by what the function evaluated at those points is going, like what it is. So as long as you have them written down, you can be like, okay, well, if these are my initial bounds and this is my next guess, I know that this is positive and this is negative. So my new bounds are going to be x of naught and x of 2. And you can ignore this one and then you move forward and keep going. That's just something that I learned and it helped me a lot to kind of keep everything organized. We kind of talked about this already. finding your updates, it's literally just the midpoint between your guesses, your bounds of A and B. And then determining for the next iteration which one's your A and which one's your B is based on the function evaluated at those bounds. Yeah. And we'll probably ask for residual and convergence for all of those. You might not be, but there's like a high chance. And then I did another problem with secant. Secant, what I did, so I think the equation in your formula sheet just gives you this from formula that I have written here. That is the Newton-Raphson formula. And then it says that where f prime of x of I equals this backwards finite difference. So all I did here was put the two together. You don't necessarily have to memorize it as long as you know what you're doing. This just kind of saves you a step of, you know, algebra, so you don't have to manipulate things so much and have a fraction inside the denominator of a fraction, because it's mad annoying. So, but yeah, I mean, I think that's pretty much it. Does anybody have any questions? Is this uploaded yet? No, Luke, it is not uploaded yet. Wanted to look at it during the review, but you're looking at it, you're in the review right now. Ugh, fine. Okay. My files are too powerful. That's a problem. Bruh. Okay, I'm uploading to the Discord right now. I don't even know why I obliged to Luke's request. He's not even nice to me. Okay, I can't upload the review yet. It's saying that my file is too powerful. So I put the practice and the practice solutions in the Discord. Where else can we find other problems to practice for the exam? That's an excellent question. Yes, Hunter is right. Homework problems. Homework problems should have some. YouTube has a lot. Numerical Methods Guy has some really great videos. You can also just look up practice problems. If you can find anything in the form of the questions that I have given you guys, you could even literally just make up your own polynomials. And as long as you can answer the same questions that I wrote in these practice ones, then you'll be able to solve it. Are we going to have that record?
I think he means recorded.
Oh yeah, it's gonna be uploaded onto web courses. Where else can we find other problems? Okay, yeah, I answered that one. Will I also upload to web courses or just Discord? I guess I could just do it onto Zoom too for those of y'all that are in here. I'll have to ask the other TAs if I'm allowed to do that because I don't necessarily know. Oh gosh, now I have to go and download them. Yeah, that's true. You will have the recording on web courses. I know it's nice to have the file sometimes too, though. So, we'll see. Do y'all want me to? Of course, Caitlin. Do y'all want me to put the files in the Zoom chat? I mean, I'll have to go in and download them, but. Okay. 1 second. I have to download them onto this computer. Okay. One. Oh, that's not it. Okay, here we go. Solutions. I need to get a webcam for my other computer so I don't have to use this tablet anymore. It's driving me nuts. Okay, 1 second. Okay, there's one. That's the blank practice questions. Those are the solutions. And then that should be the review file. Oh yeah, Hunter's absolutely right. 10 out of 10 would recommend looking up Rodrigo's review videos. Man's a king, also really good at explaining things. And a lot of my reviews are kind of based on his, mostly because he was my TA. I might even, yeah, I still even have. Oh, okay, wait. I don't even know if these are right, but I did some practice problems on my own last semester too. If y'all, do y'all want to see those? They're different, but yes, no, sure, okay. So yeah, this was my finite difference approximation practice that I did. Let's see, this one, not helpful. The example 2. I found out after I took the test that this is not the form, because I found that off of like MIT's numerical methods course. And then I was like, oh, this is not what we're doing. But yeah. So I can even zoom in a teeny tiny bit. If y'all wanted to like screenshot this or read it, I suppose. But yeah, that's just a simple one doing finite difference approximations. I don't know. I don't think example 3 is super relevant. These two were very helpful. Example 4 and example 5. So it's, again, you're literally just rearranging a polynomial. Like when y'all ask for more practice problems, they're simple enough that you can make your own. Like pretty much any function that you create yourself is going to be a valid example. Depending, like you can make it as hard or as easy as you want, you know, like add as many terms or whatever, but you know, it's not so bad, I promise. A little bisection method, boy. So here's what I'm saying about making that chart. I learned this last semester when I was going through it. I watched a video. I don't remember which one it was. It might have been numerical methods guy. I don't remember, but they talked about having this little handy dandy chart. And the more organized you can be with your work on these, because you will be asked to do more than one iteration. obviously, because it's a lot of problems. So the more organized you can be, the easier it's going to be on yourself to go back and really, I don't know, I guess successfully work through your problems, because they're multi-part problems. Well, I say that, I mean, like each section, so you have your two big math chunks that are going to be two big math problems, are going to be technically multi-step. So each question in that segment is going to be related to an iteration of one of the root solving methods. So it'll be like question 11 is, what is the updated root? And then question 12 is going to be like, what is the convergence after the first iteration, stuff like that. So the more organized you can be, the better off you'll be. So yeah, I don't even know what that means. Oh, I don't remember if I wrote that down. This number 3 right here, I recommend knowing. Highly recommend knowing. Error in storing 0.1 is round off error. That's all I'm going to say about it. It should actually, I think I even talk about it in my old review. My old review is not fantastic. I was going back looking through it and I realized there's some things that were really vague, and also a couple of things that weren't technically true. Like they weren't wrong, but they weren't detailed enough to be correct. So yeah, bear that in mind if you look at my old review. Yeah, I think that's like pretty much all of the other ones. That's decently relevant. But yeah, because this was my old review that I even snatched some stuff from. Oh, and you will have to know Horner's method, I think. Actually, I can tell you in like 2 seconds whether or not you need to. Where is she? Here's my folder. Oh, maybe you don't. Well, either way, it's easy. You might have to know it. You might not. I recommend knowing it anyway. It's broken down pretty easily. There's, if you look up on YouTube, it's actually decently simple. Yes. Oh, yeah. Big thing. So you will be taking this test, 25 questions, multiple choice, whatever, but you will be asked to submit your scratch work. So, yeah, write everything down. Technically, the only reason that, you know, we'll really be looking at your scratch work is if either your grade is suspicious or if you want to try to get points back. I recommend writing everything down, and when you submit it, because you'll have a better case, obviously, to argue if you have everything written down, because you can't just be like, oh well, I just knew, because we're not going to be able to really help you. But if you write it all down and you submit that with your scratch submission, then, you know, obviously we can help you a lot more. So yeah, that's one thing I meant to say that, but I forgot to before. But yeah. How much time do you get to submit? I think you have like 15 minutes, maybe not even that many. It's a pretty small window. It's long enough so that, you know, after you finish your test, I think the submission window for it is open from the start of the test until like maybe 10 minutes after the test is over. I guess I could look at it. Enough time so that you can scan it, I guess, is the correct answer. I can pull it up though. and one scratch paper. Oh, okay, so it's not February, that was in spring. Can we submit work from a OneNote file, or does it has to be on a piece of paper because you can't have other electronic devices. It's on lockdown. Is the test hard? No. You just have to read. You really have to read carefully. That goes for all of his exams. Like you really have to read, but yeah, this one definitely is one of those that wording can get you. So I'm trying to see the scratch paper file. It closed at 6 and the test started at 3. So I think you have 3 hours. Do you need to buy a webcam for it? I don't think you do. I'm pretty sure. No, you don't. You don't need a webcam for any of Kasab's exams or quizzes. You just need lockdown. Do they care what calculator we use? I don't know. I think we don't care what calculator you use. I mean, it'd be kind of lame if you used your phone or a computer. Actually, that's like against school policy and you get in trouble. But like other calculators, I don't really care. You don't have 3 hours to finish the test. No, you have 3 hours to submit your scratch paper. Test is during class, yes. I wonder if I have any other helpful materials for you guys. Oh, I guess I could share this. Oh, well, actually, I am already sharing it. Who am I kidding? Forgot that I was still sharing my screen. This is from Rodrigo's review. A couple of helpful tips in here. When I mentioned storing errors, that's a little tip. But yeah, okay. Any other questions for me at all? No, maybe so. Or even questions about the project, because I know project 2 is due on Sunday. So if y'all have any questions, let me know. But otherwise, I think that's it. I don't even know what's on this. No, these are just class notes from last semester. Yeah. Okay. So that's everything. The review is officially over. If anybody has any other questions, I'm going to upload these files probably to WebCourses. But they are in the Zoom chat. It actually might even be, the files might even be accessible in the Zoom recording. I don't know for sure, but what is the meaning of life? You know, I wish I knew. My life would be a lot simpler if I knew what the meaning of life was. Right now it's mini M&Ms and 42. Am I going to be available to take questions about project 2 over the weekend? Probably not. So since it's going to be due on Sunday, I mean, that's a tough question. I'm not a huge fan of receiving emails the night before projects are due. Chances are I probably will not respond if you email me Saturday night, but or message me Saturday night. I got an email from a student last week at 11:45 or something ridiculous, like 15 minutes or something before the project was due, asking me what they got wrong on it so that they could fix it for their second attempt. And it's like the audacity of this person to email me after I've made myself so available. I don't know. Grinds my gears, but it is what it is. People do be wildin'. I mean, if you message me, Danielle, at like a reasonable time on Saturday, I'll probably be able to get back to you. As for like actual meetings, no. But as long as it's at a reasonable hour, it might be. I make no promises, but I will try. Spam.
Just out of curiosity, can we review with a TA between our 2 attempts on the quiz?
Yeah, of course.
Okay, cool.
Yeah. The only thing that we don't care for is when y'all share code with each other or share results with each other. But with TAs, you know, we're happy to help. Cool. Join late. When are you posting the recording? As soon as it's done uploading and I stop recording it, I suppose. I guess I could stop recording it right now and it'll get posted. Should probably stop sharing my screen too. Do I have to end the meeting to stop the recording? I didn't think. No, there we go. Okay, we're good.